According to every official forecast, our sun should be entering a period of calm. Solar cycle 25 reached its peak in late 2024, and from that point, models predicted a steady decline in activity. By April of 2026, we were expected to be drifting quietly towards solar minimum, but our star, it seems, did not receive this message. This morning, a single sunspot unleashed 2 X-class flares in just 7 hours, propelling a shockwave toward Earth at 1,293 kilometers per second. Something is unfolding on the sun that our models failed to anticipate and are now struggling to explain. The story of what this means is still developing. As other active regions, like 4,420, continue to rotate into view, we invite you to follow along with us here on Calm Space, as solar cycle 25 refuses to follow its predicted path, and we continue to monitor these events in the days to come. In the last day, an event has taken place on the sun that is exceptionally rare. To fully grasp its implications, it is essential to look beyond the brilliant flashes of light. The flares are not the central story. Rather, they are a profound warning signal. The true narrative lies in what these eruptions reveal about the sun's current, volatile state, and what this condition might enable in the near future. The sequence began at 1:01 in the morning, Universal Time. A sunspot group, catalogued as region 4419, produced an X-class solar flare that registered X2-4 on the intensity scale. An event of this magnitude would, on any other day, have been the most significant solar news of the week. X-class flares represent the highest tier of eruption our classification system has, and even during the height of a solar maximum, we typically observe only a few of them in a given month, usually from different areas. However, this powerful flare did not occur in isolation. Approximately 7 hours later, at 8:13 inches the morning Universal Time, the very same patch of magnetic turbulence on the solar surface erupted once more. This second X-class flare was even stronger, measuring X2-5, and it originated from the exact same location as the first. Crucially, there was no significant cooldown period between these two immense releases of energy. 2 X-class flares from a single active region, separated by only 7 hours. It is a sequence of events so unusual that it elevates this far beyond a routine space weather update, suggesting a deeper instability is at play. The source of this activity, region 4419, is located at coordinates north 15, west 70 on the solar disk. This position places it near the sun's western edge, meaning it is slowly rotating out of our direct line of sight. But what makes this region so remarkable is its magnetic classification: beta, gamma, delta. This designation signifies the most volatile and complex magnetic arrangement a sunspot can possess, a kind of structural rating for profound instability. The beta component indicates it contains areas of both positive and negative magnetic polarity. Gamma adds another layer of complexity, revealing that these polarities are not cleanly separated, but are instead chaotically intermingled. Finally, the delta classification is the most critical, signifying that opposite polarities are forced so close together they exist within a single penumbra, the lighter, grey halo that encircles a sunspot's dark core. When forecasters see a beta-gamma-delta region, they know they are observing a structure that has concentrated nearly every known form of magnetic instability into one compact area. For those on Earth, the consequences of these flares arrived at the speed of light. Both eruptions generated what NOAA classifies as an R3, or strong, radio blackout, disrupting high-frequency communications across the planet's entire sunlit hemisphere. The effects were felt almost instantly. Airline pilots on polar routes, amateur radio operators, and anyone depending on shortwave signals for long-distance communication experienced disruptions within minutes. This happened because the intense burst of X-ray radiation from the flares flooded our upper atmosphere. In response, the ionosphere became significantly more conductive, causing it to absorb radio signals that would normally be reflected back toward the ground to travel across continents. It was the first direct impact from this solar storm, and it landed swiftly. What makes this series of events so scientifically compelling, however, is the behavior of the region itself. When a single area produces such repeated, high-energy outbursts without any sign of stabilization, it suggests that its underlying magnetic structure has failed to fully release its stored energy. This is a departure from the expected pattern. Normally, the physics of these eruptions involves a kind of reset. A sunspot flares, expends its energy, and then enters a quieter phase as it rebuilds. Region 4419 did not follow this script. It erupted, paused only briefly, and then erupted again. To place this in its full context, we must look at the activity leading up to these two X-class flares. In the 28 hours prior, Region 4419 had already unleashed 6 separate M-class flares. M-class events are the category directly beneath X-class, powerful in their own right and capable of causing tangible effects on our technology. This sequence of 6 M flares followed by 2 X flares paints a picture of escalating instability. This pattern does not suggest a sudden, isolated explosion. Instead, it points to a progressive and escalating destabilization of a magnetic system that is fundamentally unable to find a point of rest. In the most literal sense, this was not just 2 separate flares. The region remained in a continuous state of turmoil, undergoing multiple cycles of magnetic reconnection, where tangled field lines snap and reconfigure. With each cycle, the eruption failed to release enough energy to bring the system back into equilibrium. This is the crucial concept to understand. We are not witnessing a series of isolated events, but rather the sustained behavior of an entire magnetic structure that cannot settle down. This brings us to a question that is likely occupying the thoughts of solar physicists everywhere. If solar cycle 25 is meant to be in its declining phase, as models have consistently predicted since early 2025, then why is the sun's flare productivity actually increasing? Why are we observing some of the most volatile magnetic configurations of the entire cycle so late in the process? There is a clear discrepancy between our predictions and the sun's observed behavior, a fascinating anomaly we will explore further. For now, however, our attention must turn to the immediate consequences. NOAA's modeling teams have identified a component of the coronal mass ejection from the second flare that is partially directed toward Earth. The confirmation came from a Type 2 radio burst, a distinct radio signature that serves as undeniable evidence of a shockwave moving out through the solar corona. This tells us the second flare did more than just release light and radiation. It hurled a vast cloud of magnetized plasma into space, and a portion of that cloud is now traversing the distance to our planet. The brilliant flashes of the flares themselves have subsided, ending hours ago, but their most significant consequences are still traveling through the void. The material that was launched from the sun this morning has not yet completed its journey to Earth. The electromagnetic radiation from the solar eruption arrived at the speed of light, which explains the instantaneous onset of radio blackouts on Earth. However, the physical substance of the event, the superheated plasma, and its entrained magnetic fields, travels at a much more leisurely pace. As this material journeys across the void, the expanse of space facing our planet is, for now, quiet. It is a deceptive calm, a temporary peace that is expected to end this weekend. The true significance of the event was not the flare itself, but what that flare propelled into space, and what it launched is now on its way. To understand the extraordinary behavior of sunspot region 4419, we must explore the physics of magnetic reconnection. This is the fundamental mechanism that drives every solar flare, every coronal mass ejection, and indeed every significant space weather event that has ever posed a threat to our technological world. Magnetic reconnection occurs when magnetic field lines with opposing polarities are forced together until they snap and violently reconfigure. In that moment of realignment, the immense magnetic energy stored within the twisted structure is almost instantly converted into heat, light, and kinetic energy. A solar flare is simply the visible manifestation of this energy conversion, the X-rays, the ultraviolet light, the brilliant flash. All are signatures of the sun short-circuiting a stressed magnetic system and discharging its excess energy. Under normal circumstances, a predictable sequence follows a major flare. Having released its stored energy, the region's magnetic structure should relax into a more stable, lower energy state. The area would then enter a recovery phase, a quiet period lasting hours or even days, as it slowly rebuilds magnetic stress before potentially flaring again. What it should not do is immediately reload and unleash another flare of the same magnitude. Yet, just 7 hours after its first eruption, region 4419 did precisely that, defying all typical models of solar behavior and raising the question of how such a rapid re-energizing was even possible. The most coherent explanation for this anomaly is that the region was not a single system, but instead contained multiple, independent energy reservoirs. It can be pictured like a large building, equipped with several distinct electrical grids. If one circuit overloads and blows, the others remain unaffected and fully powered. Each of these systems can fail on its own, each can fail catastrophically, and, if the underlying stress conditions persist, they can fail in rapid succession. The region's formal classification as a beta-gamma-delta sunspot is critical to understanding this potential. In a simple, magnetically stable active region, there is typically one area of positive polarity and one of negative, separated by a single, clean boundary known as the polarity inversion line. The entire structure is relatively tidy and predictable, with a single primary failure mode. A beta-gamma-delta region, by contrast, is a far more chaotic environment. It contains multiple, often tangled and braided, polarity inversion lines, each one representing an independent and volatile point of potential failure. It is less like a building with one load-bearing wall and more like one with dozens, each under unique stresses and each capable of fracturing at any moment. This complex structure suggests that region 4419 was not a single, unified system, but rather a distributed network of stressed magnetic fields. What we observed this morning may not have been a region flaring twice in succession. Instead, we might have witnessed a process of distributed magnetic collapse, with different failure points across the network, triggering in sequence as the overall stability of the entire complex system progressively degraded. Solar physicists use a concept called magnetic helicity to quantify the degree of twisting and braiding within a region's magnetic field lines. Helicity accumulates over time as the sunspot rotates and as new magnetic flux emerges from beneath the solar surface, interacting with the fields already present. A high degree of helicity corresponds to a vast amount of stored energy. When this helicity surpasses certain critical thresholds, the region becomes susceptible to cascading failures, where a single reconnection event can create the conditions for subsequent reconnections to become even more likely. Viewed through this lens, the swarm of M-class flares observed in the 28 hours leading up to the double X-class event can be seen as precursor activities. These were smaller releases of stress, the system's failed attempts to find a stable equilibrium. It is possible that each M-class flare, rather than relieving the overall tension, simply redistributed the magnetic stress, effectively loading other parts of the region and pushing them closer to their own breaking points. When the first X-class flare finally occurred, it didn't resolve the underlying instability. It merely revealed the vast reserves of energy still waiting to be unleashed elsewhere in the structure. There is an often overlooked concept in solar physics known as flare clustering, where a single region produces multiple flares in rapid succession. This behavior can be a signature that the region is approaching a critical threshold of instability, and it is sometimes observed just before a sunspot produces its most powerful event. The implication here is deeply uncomfortable. Region 4419 may not have reached its peak. The events we witnessed could have been a partial energy release, or merely a prelude to a much larger eruption, depending on how much of the region's total magnetic energy has truly been dissipated. It is important to approach these interpretations with caution and acknowledge the limits of our current knowledge. Direct, real-time imaging of magnetic topology at the resolution needed to confirm these theories is not yet possible. Our understanding is built by inferring structure from indirect measurements, comparing solar signatures to past events, and running complex models that have their own inherent assumptions. The scenario described here is consistent with the available data, but it is not the only possible explanation. This is the nature of space weather science, a field where genuine uncertainty is the default state. Ultimately, the intricate physics of what happened on the Sun is now secondary to a more immediate concern. The flare is over, its energy release complete. But the cloud of plasma launched into interplanetary space during that second X-class event is still traveling, still moving, and heading at least partially in our direction. The speed and internal structure of that cloud, and what it might encounter on its journey to Earth, will be the factors that determine whether this event becomes a minor inconvenience or something far more serious. The story is no longer about the Sun, but about the space between us. What happened on the Sun is now a memory. The focus of our story shifts to what is currently moving through the vastness of space, a separate phenomenon with its own physics and its own profound unpredictability. The coronal mass ejection, or CME, that was launched by the X-25 flare is now journeying through the interplanetary medium. Its shock front is traveling at an estimated speed of 1,293 kilometers per second. This figure is derived from the signature of a Type II radio burst, a method that allows scientists to track the propagation of a shock wave as it travels through the Sun's corona and out into the solar wind. To appreciate this velocity, consider that the median speed for a CME is roughly 400 kilometers per second, while the solar wind itself flows at between 300 and 500 kilometers per second during quiet periods. This particular ejection is moving at more than 3 times the typical speed, marking it not just as a fast event, but as a shock-driven one. This means it is traveling faster than the ambient solar wind, plowing a pressure wave ahead of it. Much like a supersonic aircraft creates a shock cone as it moves through our atmosphere. This distinction between a slow and a shock-driven CME is critical, as it fundamentally changes what happens upon arrival at Earth. A slow-moving CME tends to drift towards our planet, gradually assimilating into the existing structure of the solar wind. Its arrival often results in only modest geomagnetic effects. A shock-driven CME, however, is a far more dramatic event. It arrives with an abrupt pressure front that compresses Earth's magnetosphere on the sun-facing side. This sudden impact can initiate a cascade of complex effects in the magnetotail, the part of our magnetic field stretching out on the night side of the planet. Even before any prolonged magnetic interaction occurs, this initial shock alone is capable of producing measurable voltage fluctuations in long conductor systems on the ground, such as power lines and pipelines. But here, the situation grows more intricate, demanding that we think in terms of interactions rather than solitary events. An earlier coronal mass ejection associated with an M-class flare on April 23rd is also currently in transit. This preceding CME is traveling at a slower pace than the shock-driven event we are now tracking. This creates a fascinating and potentially consequential scenario, depending on their exact trajectories. The faster CME has a real possibility of catching up to and interacting with the slower one somewhere in the void between the Sun and Earth. Space weather physicists have a name for this phenomenon: CME cannibalization. When a fast CME overtakes a slower one, they do not simply pass through each other like ghosts. Instead, they merge into a single, complex structure. The faster cloud of plasma compresses into the slower one, causing their respective magnetic fields to combine and restructure. The resulting entity can possess dramatically different properties than either of its precursors. Densities can rise, magnetic field strengths can amplify, and velocity gradients can become much steeper. For our purposes, the most important consequence is that the orientation of the magnetic field within this merged structure becomes highly volatile and incredibly difficult to predict. That orientation, specifically the north-south component of the interplanetary magnetic field known as BZ, is arguably the single most critical parameter in determining the severity of a geomagnetic storm. If the BZ component is pointing northward, aligned with Earth's own magnetic field at the point of impact, the CME tends to glance off the magnetosphere with minimal interaction. The effects are often minor, perhaps producing beautiful auroral displays at high latitudes, but little else. However, if the BZ component is pointing southward, making it anti-parallel to our planet's field, the outcome is entirely different. This alignment allows the incoming magnetic structure to couple directly with our magnetosphere through a process called magnetic reconnection. This opens a gateway, pouring enormous amounts of energy into our magnetic environment and driving the kind of powerful geomagnetic storms that can endanger satellites, power grids, and communication systems. The great problem with CME cannibalization is that it scrambles the BZ orientation in ways our models cannot foresee. Two CMEs, each with a benign, northward-pointing magnetic field, could merge to form a new structure with a highly volatile BZ profile that flips between orientations. If any portion of that profile is strongly southward when it reaches Earth, the resulting geomagnetic response can be far more severe than forecasters would have predicted based on either CME alone. There is a recent and powerful precedent for this kind of escalation. In May of 2024, a sequence of interacting CMEs produced what became known as the Gannon storm. This event reached G5, or extreme levels on the NOAA scale, the highest possible classification. Crucially, the initial forecast had not anticipated an event of this magnitude. The escalation occurred during transit, through the very interaction physics we are discussing. That storm generated auroras visible across much of the continental United States, caused measurable disruptions to satellite operations, and served as an unmistakable reminder of a vital truth. That truth, which runs counter to much media coverage of space weather, is that the initial flare magnitude does not determine the final storm strength. A large flare is often treated as a reliable predictor of what will follow, but it is not. The true story is written during the journey, the structure of the CME as it travels, the interactions it undergoes, and the precise magnetic configuration it possesses upon arrival. These factors can easily overshadow the influence of the original flare's energy. A moderate flare that launches a CME with a potent, southward-pointing magnetic field can cause far more geomagnetic disturbance than an extreme flare whose ejected material happens to arrive with a benign, northward-pointing field. This is where the limits of our current predictive capabilities become clear. NOAA's Space Weather Prediction Center uses a technique called ensemble modeling, which involves running dozens of simulations of the same event with slightly different initial conditions. This produces a range of possible outcomes for arrival time and intensity. For the current event, The spread in those ensemble results is wide, which tells us that the uncertainty is real and significant. This is a normal part of the process. The initial shock speed estimate, for instance, was 1,869 kilometers per second before being revised down to the current 1,293. Such revisions reflect the immense difficulty of measuring these dynamic events in real time with imperfect data. Space weather risk is fundamentally non-linear. Small differences in the input conditions can produce vast differences in the final outcome. We often do not know which inputs were most critical until after the event has passed. This is the reality that forecasters are working with, and the central concern right now is not what we have already seen, but what we might still observe in the next 72 hours. As these structures interact and finally arrive at our doorstep, the sun, after all, did not just fire once. The flare is now in a state where it is capable of erupting once more. This is a critical warning signal that we must bear in mind as we proceed with this analysis. Within the radio signature of the dual X-class event, a detailed story unfolds, one that is often overlooked in mainstream discussions. When we examine the profile of radio emissions accompanying these flares, we are seeing far more than simple confirmation of an eruption. Instead, these signals provide a rich diagnostic tool, revealing the specific nature of particle acceleration that took place. This information, in turn, tells us a great deal about the properties of the material now journeying toward our planet. Two particular kinds of radio bursts are of immense importance here. Type 2 bursts serve as the telltale sign of shock waves moving outward through the sun's atmosphere. On radio spectrograms, they manifest as features that slowly drift to lower frequencies. This drift occurs because as the shock wave travels into the less dense plasma of the outer corona, the radio emission it generates naturally shifts downward in frequency. The presence of a Type 2 burst confirms that a coronal mass ejection, or CME, has been launched with a leading shock front, and the rate of this frequency drift allows us to directly estimate the shock speed. Type 4 bursts, however, tell a different part of the story. They point to populations of energetic electrons that have become trapped inside moving magnetic structures. These electrons continue to emit radio waves as they spiral around the magnetic field lines contained within the propagating plasma cloud. When both Type 2 and Type 4 signatures appear together, it indicates an event that possesses not only a powerful shock wave, but also a substantial population of trapped energetic particles. It is precisely this combination that is known to produce some of the most significant space weather consequences. The radio burst at the 10 centimeter wavelength, associated with the X2-5 flare, was particularly noteworthy. It peaked at an intensity of 570 solar flux units, measured against a background level of just 128 units. This represents a value roughly 4.5 times the normal background emission, making it a significant anomaly. Emission at this wavelength is directly correlated with the density of electrons and the efficiency of their acceleration within the flaring region. Put simply, a stronger emission implies that a greater number of electrons were accelerated to very high energies. This detail is crucial, as a higher count of energetic electrons translates directly into a greater potential for downstream effects. These can include hazardous charging of satellite components, disruptions to communications, and increased radiation exposure for anyone flying in polar routes or living aboard the International Space Station. What we can ultimately infer from these combined radio signatures is that this event was exceptionally efficient at producing energetic particles. This is not merely about photons, the electromagnetic radiation that ceased to be a direct factor the moment it passed Earth at the speed of light. Instead, we are now concerned with a wave of protons and electrons, accelerated to energies where they can physically degrade solar panels, damage spacecraft electronics, and pose a tangible risk to human health in space and at high altitudes. Reflecting this risk, NOAA has issued a 25% probability of an S1 minor radiation storm occurring within the next 24 hours. This storm would be driven by the particle population accelerated during the flare. While not a certainty, this probability is far from negligible, and it represents a threat entirely separate from the geomagnetic storm that will come later with the CME's arrival. The radiation storm is composed of particles that travel much faster than the bulk plasma of the CME, allowing them to reach Earth in a matter of hours, not days. It's also worth noting that even before the flares, we observed an elevated flux of 2 million electron-volt electrons in the magnetosphere. These reached levels high enough to potentially cause internal charging effects in geostationary satellites. Internal charging is an often underappreciated space weather hazard. It happens when high-energy electrons penetrate a spacecraft's outer shell and accumulate charge deep inside sensitive electronics, where shielding and grounding are less effective. If enough charge builds up, it can lead to an electrostatic discharge, a miniature lightning strike that can corrupt data, damage components, or, in the most severe cases, disable a satellite entirely. While satellite operators continuously monitor this flux and can take defensive measures, there are limits to what can be done. The radio emissions are significant for another reason that frequently goes unmentioned. Beyond their effects on the ionosphere, strong radio bursts at these frequencies can directly interfere with essential technologies like radar systems, GPS signals, and high-frequency communications. It is a problem of signal to noise. Imagine a sensitive dish antenna attempting to track a faint satellite signal while the sun itself suddenly brightens to become a radio source hundreds of times more powerful. Filtering out that level of interference is an immense technical challenge. Military radar installations, air traffic control, and maritime communication systems all must contend with this reality when a major solar flare occurs. We have, of course, already witnessed the R3 level radio blackout from this event, which happened in real time as the flare's X-ray emissions arrived at the speed of light. That was the first phase of impact, and it is now over. The ionosphere is recovering, and high-frequency communications are gradually returning to normal. But this brings us to a crucial point. The second phase has not yet begun. The geomagnetic response, the part driven by the physical arrival of the CME, is still to come. The timing of this is critical, as it means we are currently in a temporary lull, with the full consequences of this event still in transit across the solar system. This calm is deceptive. If you were to check a space weather report right now, you might conclude that all is well, and at this precise moment, that is technically true. But the conditions we are experiencing are not a stable state. They are a waiting state. At the time of this recording, solar wind conditions near Earth are remarkably placid. The wind speed is hovering around 383 kilometers per second and is, in fact, showing a slight decrease. The total strength of the interplanetary magnetic field, which we call BT, is low, sitting near 4 nanoteslas. Its crucial north-south component, BZ, is fluctuating weakly around zero, showing no sustained southward or northward orientation. Consequently, the planetary K index, the most common measure of global geomagnetic disturbance, is at a value of approximately 1.3. This is a state of quiet, almost bordering on boring. There is currently no geomagnetic stress being exerted on Earth's magnetosphere, none at all. And that is precisely what makes this moment so profound. The sun has already acted. The consequences are already on their way. Yet, as you listen to this, Earth is enveloped in a period of unusual calm. With roughly 93 million miles of space still separating our world from the approaching plasma cloud. This period of quiet actually has a formal name in the field of space weather physics. It is known as the preconditioning state. The way the magnetosphere is preconditioned before a CME arrives has a direct influence on how it will ultimately respond to the impact. The The state of our planet's magnetic shield is not merely a passive backdrop, it is an active variable in the equation of the coming storm. This raises a vital question. Is the magnetosphere currently in a relaxed state that might render it more vulnerable, or could this quiet preconditioning somehow soften the blow that is yet to come? It's a detail often overlooked in broader discussions, yet it carries immense physical weight. Earth's magnetosphere is not a static shield, but a living system, with its own internal currents, populations of trapped particles, and unique pressure distributions. How it reacts to a coronal mass ejection depends profoundly on the state it was in at the moment of impact. A magnetosphere already under stress from days of high solar wind activity might absorb a new blow with a surprisingly muted response. In contrast, a relaxed, quiet magnetosphere, like the one we find ourselves in now, could react far more sharply to a sudden surge of pressure. The underlying mathematics are incredibly complex, making outcomes difficult to forecast with certainty, but the general principle is well understood. This presents two distinct possibilities. In one scenario, the magnetosphere's current calm allows it to act like a cushion, compressing on its sunward side and dissipating the energy internally, keeping the geomagnetic disturbance within the predicted G1 to G2 range. But in a second, more concerning scenario, that same calm state could actually amplify the event. The lack of pre-existing pressure might allow the incoming shock to compress the magnetic field more severely than it otherwise would, triggering a much larger initial disturbance and potentially paving the way for a more intense storm. We simply cannot know which path events will take until the CME arrives and its properties are measured directly, a fundamental limitation of modern space weather prediction. We are forecasting an event whose most critical variables remain unknown until it is already upon us. Adding another layer of complexity to this picture is a high-speed stream of solar wind flowing from a feature on the Sun known as a coronal hole. These are areas where the Sun's magnetic field lines open directly into space instead of looping back, creating a channel for solar wind to escape at much higher velocities. This stream is projected to arrive at Earth within the same general timeframe as the CME, though whether their arrivals will overlap or be sequential is still uncertain. This question of timing is not a minor detail. Slight differences in the sequence can lead to dramatically different outcomes on Earth. When a CME travels through a pre-existing environment of fast-moving solar wind, the interaction can be especially disruptive. The trailing edge of the CME can become compressed by the faster stream pushing from behind, which in turn intensifies the density and magnetic field structures within that region. A geomagnetic disturbance that might have otherwise faded in 12 hours could be extended to 36 hours, or even longer, as our magnetosphere is forced to process one wave of energy after another. It's a situation where multiple moderate inputs can combine to create a geomagnetic response far greater than the sum of their individual parts. The Space Weather Prediction Center, SWPC, has timed the expected arrival for the late hours of April 25th into April 26th. Official forecasts anticipate G1 minor storm conditions, with a reasonable chance of reaching G2 moderate levels. It is crucial to understand, however, that these are baseline predictions. They are built on the assumption of relatively harmless CME characteristics and no significant interaction effects. Should the scenario of a CME merger unfold, or if the magnetic field component known as BZ arrives strongly southward, or if the coronal hole stream amplifies the impact, we could certainly witness storm levels that exceed these forecasts. On the other hand, if the geometry of the arrival is favorable, the storm could easily underperform the baseline prediction. This wide range of possibilities is not a sign of forecasters being non-committal. It is a direct reflection of the genuine uncertainty embedded within the underlying physics. Predicting space weather is a challenge on par with forecasting the intensity of a hurricane. You can narrow the cone of probability, but you can never completely eliminate it. The energy from this event is already traversing the void between the Sun and Earth. The final decisions about how that energy will influence our planet are not being made by forecasters, but by the laws of physics, unfolding in ways we cannot fully observe until the process is already underway. Yet, there is a piece of this puzzle that brings the entire picture into sharper focus. The most critical part of this story is not the event that has already occurred. It is not the CME that is currently in transit. The most important part is what remains on the solar disk right now facing us, loaded with energy and intensely active. While we track the CME from the recent X2-5 flare, 3 separate active regions on the Sun's face possess the capability to unleash new eruptions. Some of these are positioned in geometries far more directly aimed at Earth than region 4419 ever was. What is on the solar disk at this moment matters more than what has already left it, and that is where our attention must turn next. The central thread weaving through this entire narrative, the crucial point to grasp, is that the dual X flare from region 4419 is not the primary danger. Instead, it should be seen as evidence. It is powerful evidence of what the Sun's current configuration is truly capable of producing. To understand why that evidence is so significant, we must examine what else is currently loaded and aimed in our direction on the solar disk. The simple truth is that region 4419 is not acting alone. As of this moment, the Earth-facing side of the Sun is host to 3 distinct active regions that carry the volatile beta-delta or beta-gamma-delta magnetic classifications. There is region 4419, which we have already discussed, now sitting near the Sun's western limb. Then there is region 4420, which is currently rotating toward the central meridian, the line that runs down the middle of the solar disk from our perspective. And finally, there is region 4423, a newly emerged area that is already unleashing M-class activity, despite being so young that its sunspot structure has barely had time to stabilize. To have 3 of these magnetically complex delta regions on one solar disk, all at the same time, is a remarkable development. This delta classification matters more than perhaps any other single parameter when it comes to forecasting the likelihood of X-class flares. Time and again, statistical studies covering multiple solar cycles have confirmed a powerful correlation. These delta-type sunspot regions are responsible for the overwhelming majority of the most powerful and energetic solar events. While a region lacking a delta structure can certainly still produce flares, the probability distribution shifts dramatically, favoring much smaller events. But once you introduce that complex delta structure into the magnetic mix, you effectively unlock the upper end of the flare energy spectrum, making the most extreme outbursts possible. During an active phase of the solar cycle, having a single active delta region on the disk is not particularly unusual. The presence of 2 at once would be considered noteworthy, but to have 3 appearing simultaneously is a genuinely rare occurrence. This is precisely the kind of configuration that space weather forecasters flag internally, a situation that represents an elevated baseline risk. It signals a period where the potential for major solar activity is significantly higher than normal, demanding our continued and careful observation. The current solar activity presents a curious and elevated sense of risk. This isn't because a specific region is on the verge of producing an X-class flare in the immediate future, but rather because the collective probability of such an event occurring somewhere on the solar disk in the coming days is significantly higher than usual. This pattern of multi-region activity reveals something fundamental about the Sun's present state, something that extends beyond the behavior of any one sunspot. The solar surface is not merely experiencing a localized disturbance, it is displaying a broad, global magnetic instability that is distributed across multiple areas. It suggests that the underlying physical process charging these regions with energy is acting coherently over vast portions of the Sun, a far cry from the isolated instabilities seen during quieter solar phases. The dual X-flare event was a product of this exact configuration. And there is no compelling reason to believe this setup cannot trigger similar events from the other active regions, particularly if one of them reaches the same critical threshold that region 4419 apparently crossed. The window of concern, therefore, is not the next few hours, but the next 1 to 2 weeks. Within this time frame, any of these three regions could escalate from producing M-class flares to unleashing powerful X-class events. The geometry of each region's position will ultimately decide how directly any resulting coronal mass ejection might strike Earth. What we witnessed from region 4419 was more than just a local eruption. It was a profound proof of concept. It demonstrated that the Sun's current magnetic arrangement is fully capable of generating successive X-class flares from a single region in a short period. It also serves as a powerful reminder that similar events could originate from the other regions that share this unstable configuration. This is the crucial idea to bear in mind as we consider what these other regions might do, because the one that warrants our most careful observation is not the one that has already erupted. Region 4420 is, at present, the largest active region on the Sun, covering an area of approximately 250 millionths of the solar hemisphere, a standard unit for measuring sunspot group size. This makes it substantially larger than region 4419 was when it produced its recent X-class flares. Region 4420 is a complex system, containing roughly 20 individual sunspots scattered across an intricate magnetic structure. Over the past several days, the shear between its polarity regions has been steadily increasing, a sign of growing instability. This entire region is on the move, rotating steadily toward the Sun's central meridian. This is an imaginary line that runs from north to south across the solar face from our perspective on Earth. The position of an active region relative to this line is critically important. When a region is near the central meridian, any coronal mass ejection it produces is maximally Earth-directed. The resulting plasma cloud travels almost directly along the Sun-Earth line, ensuring our planet is squarely in the middle of its path. At the moment, region 4420 is assessed to have a lower X-class flare probability than region 4419 did before its recent events. But such an assessment is merely a snapshot in time. The truly relevant factor is the trend. Region 4420's magnetic complexity is on the rise. More sunspots are emerging. The shear between polarities is intensifying, and its delta structure is strengthening. All of these indicators suggest the region is in a build-up phase, accumulating energy rather than remaining stable or decaying. While not an absolute certainty, as some complex regions can stabilize without major events, the correlation between rising complexity and subsequent X-class flares is strong. This is why forecasters adjust their probability estimates upward as this growth continues. If region 4420 were to follow the same trajectory that region 4419 did over the last week, we could anticipate a clear pattern. This would likely involve several days of M-class activity growing in frequency, a continued buildup of magnetic complexity, and one or more precursor events that shift stress without a full release. This would all culminate in a major X-class event, potentially followed by more large flares. If the region, like 4419, contains multiple reservoirs of energy, the critical difference, however, lies in the geometry. Region 4419 produced its X-class flares when it was positioned at West 70, meaning it was already well past the central meridian and rotating toward the Sun's far side. Any CME launched from that position travels at a significant angle away from the Earth-Sun line. While today's CME has an Earth-directed component, it is only partial, as the main thrust of the ejection is aimed westward of our planet. Should region 4420 produce a similar event in the coming days, it would likely do so from a position much closer to the central meridian. This means it would be fully Earth-facing, with no glancing geometry or partial components. The entire path of such a CME would intersect Earth's orbit almost directly, and the implications of that direct geometry for the intensity of a geomagnetic storm are substantial. This is precisely why region 4420 matters more than the region that has already fired. The first region has already played its part, and we are now simply observing the consequences unfold. Region 4420, on the other hand, has not yet shown its hand. If it does, and if it does so with an energy release comparable to what we saw from region 4419, the geometry will transform what was a partial event into a full, direct impact. Region 4419 was the test case. Region 4420 is the potential repeat performance, but this time with the stage lights pointed directly at the audience. While our attention is rightly focused on region 4419's aftermath and region 4420's approach, a third area on the disk introduces an element of unpredictability. This sleeper variable, region 4423, is a newly formed active region that has been growing with remarkable speed over the last few days. It has expanded from virtually nothing into a recognizable sunspot group with a beta-delta magnetic structure. Most notably, it has already produced an M-class flare in its short existence. A much faster development of flare productivity than is typical for emerging regions. It seems this region emerged already primed for activity. Regions usually require a week or more to mature into significant flare producers, yet region 4423 accomplished this in a matter of days. The fact that it already possesses a delta configuration at such a young age suggests that the magnetic structure rising from beneath the solar surface was loaded with the kind of complexity that fuels major flares right from the very beginning. The emergence of active region 4423 was unusual. It did not gradually develop a delta structure, it arrived with one already formed. This detail is significant, suggesting that the energy source fueling this area is substantial and deliberate, not merely incidental. It points to a region with the capacity for continued development, one that could become a producer of serious flares over the coming week or two. For forecasters, however, such emerging regions pose a unique challenge. Without an established history, there is no baseline for their typical behavior, no record of how they accumulate stress or what their flare rates might be. Any assessment requires historical observation, which, for region 4423, is almost entirely absent. Our predictions, therefore, must rely on analogies drawn from observations of other emerging delta regions from the past. There is a compelling, though still speculative, hypothesis that deserves consideration. It posits that multiple active regions on the solar disk may not evolve as independent entities. Instead, large-scale magnetic connections within the corona could link these regions, allowing stress in one area to influence the stability of another. This raises a fascinating question. Could region 4423 be magnetically tied to region 4420, or even to the remnants of 4419? If so, an event in one location might trigger or contribute to instabilities across the solar surface. This concept of the Sun as an interconnected system, rather than a collection of isolated phenomena, is gaining support. It would offer a powerful explanation for events like sympathetic flaring, where physically separate regions erupt in quick succession. If this hypothesis holds true, the simultaneous presence of 3 delta regions is not just a statistical anomaly. It is a configuration that may elevate the probability of coupled behavior, where one region's collapse could propagate through the system. The uncertainty surrounding region 4423 is a double-edged sword. On one hand, it might simply continue producing moderate M-class flares, maturing into a standard active region without ever crossing the threshold for a major X-class event. This would be the most unremarkable outcome. On the other hand, its rapid formation and pre-existing delta structure mean it could escalate far more quickly than anticipated, unleashing a major event with very little warning. The primary danger here is the element of surprise. An X-class flare from region 4,423 inches the next week would be more difficult to foresee than one from the other 2 regions, precisely because its patterns of behavior are still being established. And in the world of space weather, it is these unexpected events that are most likely to catch infrastructure operators unprepared. Everything about the current solar environment, the activity across multiple regions, the complex delta configurations, and the swift development of new areas supports the conclusion that the dual X flare from region 4419 was not a final act. Instead, it appears to have been the opening of a new window of risk. The Sun has demonstrated its potential in this configuration, and the other active regions are continuing to build the same kind of complexity that made that demonstration possible. The next major flare could originate from a region we have been watching closely, like 4420, or it could erupt from a region we are still struggling to characterize, like 4423. This very unpredictability has become a central component of the overall risk profile. To truly grasp the nature of the current threat window, it is essential to understand the fundamental rhythm of the Sun, its rotation. From our vantage point on Earth, the Sun completes a full rotation in approximately 27 days. This steady turning means that every active region on the solar disk is constantly moving across our field of view, journeying from the eastern limb to the western limb over a period of roughly 2 weeks. This celestial clockwork is critically important because a region's geo-effectiveness, its ability to affect Earth with space weather, is almost entirely dependent on its rotational position. An active region's location determines the trajectory of any material it ejects. A region just rotating into view near the eastern limb is facing generally away from us. Any flare or coronal mass ejection it produces will send material largely to the east of the Sun-Earth line. Similarly, a region near the western limb, like 4419 this morning, is about to disappear from view, and its ejector will travel mostly to the west. It is only when regions are near the central meridian, the imaginary line running down the center of the solar disk, that their ejector travels along a path closely aligned with our planet. This is the geo-effective window, where even a modest event can have significant geomagnetic consequences because its energy is aimed directly at us. This rotational clock governs the current sequence of events. Region 4419, the source of the recent flares, is now past the central meridian and moving toward the western limb. Any future flares from this region will become progressively less geo-effective as it rotates away. Within a few days, it will be gone from our view entirely. Meanwhile, region 4420 is currently approaching the central meridian. Over the next 4 to 11 days, it will pass through its zone of peak geo-effectiveness. A major flare during this window would launch ejector directly toward Earth. Following behind is the newcomer, region 4423. While still in a growth phase, Its current trajectory suggests it will also transit through the geo-effective zone sometime in the next 1 to 2 weeks, presenting another period of potential Earth-directed activity. The risk we face is not evolving in a straight line. It is unfolding in time with the Sun's rotation. The threat from region 4419 is now diminishing due to its position. In its place, the next several days will bring the largest active region, 4420, into a position where its potential impact on Earth is maximized. After that, region 4423 may follow suit. This is why the real danger is not the flare that has already happened, but the flares from regions that are now rotating into direct alignment with Earth. The Sun's rotation is the clock, and we are in the early hours of a threat window that will remain elevated until these complex regions either unleash their energy or rotate safely past the geo-effective zone. To understand the approaching solar event, it is essential to establish a clear and realistic baseline. This helps us navigate between the extremes of alarm and indifference. According to NOAA's Space Weather Prediction Center, the baseline forecast for the CME's arrival late on April 25th and into April 26th is for a G1 minor geomagnetic storm. There is a reasonable chance this could escalate to a G2 moderate storm, particularly if various solar phenomena interact and amplify the effect. By space weather standards, this is a relatively manageable scenario. In practical terms, a G1 or G2 storm manifests as auroras appearing at lower latitudes than usual, perhaps becoming visible across the northern United States and parts of northern Europe. At high latitudes, minor voltage fluctuations may occur in power grids, but these are well within the safety margins of modern infrastructure. Similarly, slight disruptions to GPS accuracy might affect high-precision surveying applications, but not everyday navigation. High-frequency radio and satellite operations could also see minor impacts, with some increased drag on satellites in low Earth orbit, possibly requiring small course corrections. For most of humanity, these events are entirely imperceptible. Such storms happen several times a year during the Sun's active periods, and daily life continues uninterrupted. It's a reminder that the impact of space weather is a matter of perspective. An exciting opportunity for aurora chasers, a logistical nuisance for satellite operators, and a routine monitoring task for grid engineers. The baseline forecast does not point to a societal collapse, but rather to an event our systems are built to withstand. However, a baseline forecast is just that, a baseline. It represents the most likely outcome if all the variables behave as predicted, without any unforeseen complications. But in this case, at least 2 potential amplifiers could push the storm's intensity beyond this initial estimate. The first of these is the possible interaction between the CMEs themselves. If the faster CME from the X2 5 flare catches up to and merges with the slower one from the earlier M-class flare, they could form a single, combined plasma cloud. Such a merger could create a structure with properties far more potent than either CME individually, featuring higher density, a more powerful magnetic field, and a dangerously unpredictable BZ orientation. This raises a crucial question. How will this cosmic collision unfold? Depending on the specifics of the merger, a G1 storm could easily become a G2, or a G2 could be elevated to a G3. The second potential amplifier is a high-speed stream of solar wind emanating from a coronal hole. Should this stream arrive at Earth in the same time frame as the CME, it could act to compress and sustain the geomagnetic disturbance. This would affect both the storm's intensity and its longevity. For instance, a disturbance that might have lasted for 6 hours as a G2 event could be extended to 18 hours. Or it could be briefly pushed to G3 levels during the period of maximum compression. This illustrates that the baseline forecast should be seen as a minimum threshold, not a maximum limit. The true outcome hinges on dynamic interactions that are impossible to predict with certainty before they happen. This isn't an attempt to hedge a forecast. It is the fundamental nature of predicting space weather. What remains certain is that a geomagnetic storm will occur this weekend. The great uncertainty lies in its final character. Will it be a minor event that passes without notice, a moderate one with some tangible effects, or something more significant if these amplifying factors align? The core narrative has not changed. The sun has delivered a warning shot, and the effects of that shot are now in transit. Crucially, the volatile solar conditions that enabled this event persist, meaning more activity could follow, potentially compounding whatever this weekend brings. We may be witnessing an opening act, not the main event. To truly grasp the risks, we must delve into the physics of how coronal mass ejections interact with one another. This field is one of the most active and challenging frontiers in space weather research. The difficulty lies in the fact that these crucial interactions unfold in the vast expanse of interplanetary space, a region where our ability to make direct observations is extremely limited. We are, in a sense, trying to understand a process that happens largely out of sight. When two of these massive plasma clouds meet in their journey through space, a complex series of events is set in motion. The magnetic fields embedded within each CME begin to tangle and reconfigure, with field lines from one cloud breaking and reconnecting with the other. If the CMEs are preceded by shock fronts, these can merge into a single, more powerful shock wave, or create intricate, multi-layered shock structures. At the boundary where they collide, the plasma becomes compressed, creating zones of unusually high density that can dramatically alter how the combined cloud later delivers its energy to Earth's magnetic field. For those predicting the practical impacts on Earth, however, the most critical change involves the magnetic orientation known as BZ. A merged CME can have a BZ component that is far more volatile and variable than either of its parent CMEs. A cloud that was originally on a trajectory to deliver a stable, northward-oriented magnetic field, which is largely harmless, can be transformed by the interaction into one that flips its orientation repeatedly. Each time the field flips southward, it can trigger a fresh injection of energy into our planet's magnetosphere. A series of these southward BZ episodes can drive a cumulative geomagnetic disturbance far more severe than what either CME could have produced on its own. This creates a forecasting problem of immense difficulty. Our instruments include coronagraphs, which allow us to see a CME as it erupts from the sun, and spacecraft positioned at the L1 Lagrange point, about 1 million miles from Earth. These L1 monitors can measure the properties of the solar wind just before it reaches us, providing a crucial 30 to 60 minute warning. But the enormous volume of space between the sun and the L1 point remains a virtual blind spot. While we can create sophisticated models to simulate what might be happening during the CME's transit, we cannot observe the process directly with the precision needed to see these critical interactions as they occur. The consequence of this observational gap is profound. It means the most dangerous and transformative effects of a CME merger can only be confirmed after the process is complete. By the time our sensors at the L1 point detect a complex, merged cloud, the interaction has already taken place far from our view. We are left with only a brief warning before a potentially amplified and far more complex storm makes contact with our world. The BZ profile that we measure upon arrival is the one we must endure. While forecasters can alert satellite and grid operators to what is approaching, the fundamental nature of the incoming disturbance cannot be altered. This stands in stark contrast to the behavior of isolated coronal mass ejections. A single CME, when well defined by coronagraph data and transit models, allows for a forecast with relatively tight margins of error. its arrival time can be predicted to within a few hours, and its intensity can be estimated within a factor of 2. Even the orientation of its BZ component can be inferred, albeit imperfectly, from the magnetic structure of its solar source region. However, with interacting CMEs, all of these predictions become significantly less certain. The window for arrival time widens, and the potential intensity can fluctuate by more than a factor of 2. Most critically, the BZ orientation becomes exceptionally difficult to anticipate. For this particular event, the question of whether the X-25 CME will overtake and merge with the preceding M-class ejection is still an open one. Some model simulations suggest a merger will occur, while others predict 2 sequential arrivals without significant interaction. The truth of the matter will only be revealed when both structures reach the L1 Lagrange point, where our instruments can take direct measurements. The central narrative, however, remains unchanged. The Sun has unleashed a major event, and the consequences are evolving as they propagate through the interplanetary medium. What began as a forecast for a single relatively predictable event with one trajectory and one set of expected effects has morphed into a far more complex scenario. It now involves multiple, potentially interacting structures whose physics could amplify their impact. This introduces a layer of uncertainty that we cannot fully resolve until the event is nearly upon us. Adding another layer of complexity, a different solar feature may already be amplifying the situation in ways that will only become apparent when it combines with the other incoming structures. This is where we must consider the influence of coronal hole streams. Earlier, we noted the presence of a high-speed solar wind stream flowing from a coronal hole on the Sunday. It is worth revisiting this phenomenon, as it is a factor often overlooked in mainstream space weather discussions, but one that can dramatically alter how a CME affects our planet. Coronal holes are regions in the Sun's atmosphere where the magnetic field lines are open, extending far out into space instead of looping back to the solar surface. In closed field regions, these magnetic loops trap plasma near the Sunday. But in the open field configuration of a coronal hole, this plasma can escape much more easily along the extended field lines. It is a feature that fundamentally changes the solar wind itself. The solar wind emanating from these holes is faster, hotter, and less dense than the slow solar wind originating from closed field areas. When a high-speed stream from a coronal hole reaches Earth by itself, it generally produces only modest geomagnetic effects, typically causing storms at the G1 or occasionally G2 level. It represents a fairly common source of minor disturbances and is a primary driver of what is known as recurrent geomagnetic activity. This is because coronal holes can persist for several solar rotations, generating similar stream events approximately every 27 days. The dynamic changes, however, when a high-speed stream arrives at Earth at roughly the same time as a CME. The interaction between the two can amplify the overall geomagnetic response. Specifically, if a CME is followed closely by a high-speed stream, that stream can compress the CME's trailing edge. This compression intensifies the density and magnetic field structures within that part of the CME. As a result, a geomagnetic disturbance that might have otherwise subsided in 12 to 24 hours could be extended to 36 hours or more, as Earth's magnetosphere must contend with the prolonged pressure from the compressed structure. For the current event, the timing of the coronal hole stream's arrival is expected to coincide with the latter part of the CME impact window. This potential overlap is what creates such uncertainty. If the stream arrives during the peak of the CME's impact, we could witness significantly extended storm durations. Conversely, if it arrives after the main body of the CME has already passed, it might only trigger a secondary, smaller disturbance without amplifying the primary event. The precise timing is therefore critical, yet it is something our models can only estimate. This situation underscores a broader principle. Space weather events rarely occur in isolation. The environment of near-Earth space is shaped by everything happening on the Sun at once. Multiple moderate events arriving in close succession or overlapping can produce outcomes that are non-linear, meaning their combined effect is greater than the sum of their parts. A standalone G1 event could be amplified into an extended G2 storm under the right conditions, just as a G2 event might be pushed briefly into the G3 category. What the active region has demonstrated, and what the broader solar configuration suggests, is that our star is currently producing repeated, moderate to strong inputs into our planetary environment. Any single input might be manageable on its own, but the cumulative exposure to multiple events in rapid succession can place immense stress on systems designed with the assumption of isolated disturbances. This is the core of the current challenge. The danger lies not in any single eruption, but in the accumulation of events and the complex interactions between them, all occurring in an environment that is far more active than baseline forecasts anticipated. Of all the variables that determine the severity of a geomagnetic storm, the one that matters most is paradoxically the one we are least equipped to predict. It is a parameter known as BZ. If you have not encountered this term before, it is likely by design. BZ rarely appears in mainstream news coverage because it is invisible, counterintuitive, and resists the simple narratives that space weather reporting often seeks to provide. Yet, it is the single hidden factor that will determine whether this storm is a minor disruption or something far more significant. Understanding what BZ is and why it remains so unpredictable is key to grasping why forecasters are exercising such caution about the days ahead. BZ represents the north-south orientation of the magnetic field carried within the solar wind, or a coronal mass ejection, as it arrives at Earth. Every cloud of solar plasma transports its own magnetic field, which is threaded through it, essentially frozen into the ionized gas by fundamental physics. This embedded field has three components, one pointing along the Sun-Earth line, another pointing east-west, and the third, the one that concerns us most, pointing either north or south. This third and most crucial component is BZ. It is this invisible alignment that holds the key to the storm's ultimate power. On its sun-facing side, where it meets the constant stream of the solar wind, Earth's magnetic field is oriented northward. This specific alignment has been our planet's primary defense against solar radiation for billions of years, creating a magnetosphere that guides charged particles around us. When the solar wind's own magnetic field, its BZ component, is also pointing northward, the two fields are parallel. In this configuration, they fail to couple efficiently. The solar wind simply glides past our magnetosphere, much like water flowing around a smooth stone, transferring almost no energy into our magnetic environment. Regardless of the solar wind's speed or density, or how dramatic a solar flare may have appeared, geomagnetic activity remains low. A coronal mass ejection traveling at 10 million miles per hour with a northward BZ will elicit little more than a shrug from our planet's defenses. Aurora watchers are left disappointed, and grid operators can relax. However, the situation transforms entirely when the incoming BZ component is oriented southward. Now, the two magnetic fields are anti-parallel, pointing in opposite directions. When this occurs, they do what anti-parallel fields in a plasma environment always do. They reconnect. The field lines break and then rejoin in a new arrangement, effectively opening a gateway in the barrier between the solar wind and our magnetosphere. Through this opening, a flood of energy pours in. Particles are accelerated to high speeds, and powerful currents surge through the upper atmosphere. The magnetosphere itself is dramatically reshaped, compressed on the sunward side and stretched into a long tail on the night side. All of this restructuring unleashes vast amounts of energy back toward Earth. The stronger the southward BZ, and the longer it holds that orientation, the more energy is absorbed, and the more powerful the resulting geomagnetic storm becomes. In essence, every significant geomagnetic storm ever recorded has been fueled by sustained and strong southward BZ conditions. The critical factor is not the size of the flare, nor the speed of the CME alone, but this specific magnetic orientation. And this brings us to a deeply frustrating challenge at the heart of space weather forecasting. We cannot reliably determine what the BZ will be upon impact until we can directly measure it. These measurements are taken at the Lagrange 1 point, a point of gravitational stability about 1 million miles upstream from Earth, where spacecraft constantly monitor the incoming solar wind. This provides us with a warning window of only about 30 to 60 minutes before the plasma reaches our planet. That brief interval is all the time we have between knowing a storm is on its way and understanding how severe it will truly be. The reason we cannot predict this crucial parameter sooner lies in the profound complexity of a CME's magnetic structure, which is constantly evolving during its journey. When a CME erupts from the Sun, its magnetic field is a reflection of the twisted, sheared geometry of its source region, often forming a flux rope structure resembling a tightly wound spring of magnetic field lines. But as this magnetic cloud travels through interplanetary space, it is not a static object. It is a dynamic, evolving entity that rotates, expands, and interacts with the ambient solar wind, other CMEs, and high-speed streams. This journey can cause the structure to twist, flip, compress, or even fragment. By the time it arrives at Earth, its magnetic configuration might only vaguely resemble the one it had at its solar departure. Solar physicists have developed methods to infer the likely BZ orientation by studying the source region on the Sun itself, analyzing sunspot structures, polarity distributions, and the orientation of the polarity inversion line. When conditions align perfectly, these estimates can be reasonably accurate, yet the margin for error remains wide. This is the central challenge for forecasters. A CME that leaves the Sun with what appears to be a dominant northward magnetic field can rotate in transit or interact with other plasma in ways that produce a southward BZ at Earth. The opposite is also true. A forecast for a strong southward BZ can materialize as a mostly northward field when the cloud actually arrives. While prediction skill for this parameter has improved over the decades, it still lags behind nearly every other aspect of space weather forecasting. This is precisely why forecasts for storm intensity always come with significant uncertainty. We can determine the size of the event, we know its speed within a reasonable margin. We can even estimate its arrival time, usually within a window of about 6 hours. But the one thing we cannot know until just 30 to 60 minutes before impact is whether the event will trigger a major storm or a minor one. The distinction between a G1 storm, which is barely noticeable, and a G4 storm, with the potential for serious infrastructure consequences, can hinge entirely on the simple up or down orientation of the BZ field as the plasma cloud makes contact. This uncertainty is not a problem that can be solved by better computer models or more data. It is a result of the genuine physical unpredictability of a magnetic field evolving as it passes through a turbulent, structured medium that we cannot observe in detail. For the current event, the BZ prediction is especially uncertain, with compounding factors that are important to understand. If the CME from the X2 5 flare merges with the earlier M-class CME, as some models suggest, the magnetic structure arriving at Earth will be a combined cloud. Its properties will be different from either of its parent events. This merging process effectively scrambles the BZ, as field lines from one cloud reconnect with those of the other. The resulting structure could contain multiple reversals of orientation packed into a single transit. The BZ profile sweeping past the L1 point could then flip direction several times, creating a storm that ramps up, subsides, and then intensifies again in a way that events with sustained BZ never do. Adding another layer of complication is the coronal hole high-speed stream. Should this stream arrive at roughly the same time as the CME, it would compress the CME's trailing edge against the slower solar wind ahead of it. This compression could intensify the magnetic structures in that region, making the BZ behavior even more variable and erratic. These multiple, interacting factors do more than just widen the range of uncertainty. They fundamentally alter the nature of the forecast itself. We move from a relatively predictable single event scenario to a genuinely difficult combined event forecast, complete with multiple potential failure modes, each carrying its own probability and potential impact. Ultimately, a storm's true character is not defined at its solar launch, but in the final, crucial moments of its arrival at Earth. This single idea holds a profound truth about the nature of space weather. While metrics like flare size, shock speed, and the intensity of radio bursts often capture headlines during a major solar event, they only describe the eruption at its source. These parameters are certainly useful. They are not mere noise, but they do not dictate the ultimate geomagnetic effect on Earth. That response is governed almost entirely by what the interplanetary magnetic field's north-south component, known as BZ, does when the plasma cloud finally reaches our planet. And BZ is a hidden variable, one we cannot measure in advance. We can only observe its orientation in the final 30 minutes before impact, a critical but fleeting window of warning. This inherent uncertainty is why even seemingly minor storms are significant in the current solar environment. They do not occur in a vacuum. Instead, they are unfolding against the backdrop of a highly active sun with multiple regions producing coordinated activity across its visible disk. This is happening during a solar cycle that has defied predictions of its decline for well over a year. The effects of these events can therefore compound in ways a single eruption cannot. A G1 storm, followed by another, and then a surprise G3 storm when the BZ component turns sharply southward, creates a cumulative stress that no one event would have caused alone. The central thread of this entire analysis leads us to this conclusion. The sun has already fired, more events are probable, and the one variable that will determine their severity is the one we cannot see until it is already upon us. Satellites, it turns out, are the weakest link in this chain. Low Earth orbit is now more densely populated than at any other moment in human history. This is not hyperbole. It is a simple statement of fact, describing a situation that has evolved more in the last 5 years than in the preceding 50. Today, approximately 11,000 active satellites circle our planet at altitudes between 160 and 2,000 kilometers. The vast majority belong to the Starlink constellation, with a growing number of similar commercial broadband networks from operators like Amazon, OneWeb, Chinese state providers, and several other companies aspiring to build their own mega constellations. To truly appreciate this scale, consider that as recently as 2019, the total number of active satellites across all orbits was less than 2,000. In under 7 years, we have added more than 5 times that number to low Earth orbit alone, and the rate of deployment continues to accelerate. This unprecedented density has fundamentally changed how space weather events translate into real-world infrastructure risk. The old calculus, where a solar storm might affect a relatively small number of expensive, heavily shielded, and professionally managed spacecraft, has been completely overturned. It has been replaced by a new reality, where the same storm now threatens vast commercial constellations of comparatively simple satellites that operate with very thin margins for error. An event that would have been a mere operational inconvenience for a dozen geostationary satellites in 2010 can now simultaneously impact thousands of satellites at low altitudes. The economic exposure from this shift is dramatically different, raising new questions about the sustainability of our modern space infrastructure. To grasp why, one must understand what physically happens to a satellite during a geomagnetic storm. When the Earth's magnetosphere absorbs energy from the solar wind, it causes the upper atmosphere, specifically the thermosphere, at altitudes from roughly 80 to 600 kilometers, to heat up dramatically. This heating forces the atmosphere to expand outward. As a result, at any given altitude within that range, the atmospheric density increases substantially. During a major storm, the density at an altitude of 400 kilometers can easily double or triple, and sometimes more. Any satellite traveling through this newly thickened atmosphere will experience a proportional increase in drag. In the precise world of orbital mechanics, drag is the constant enemy of sustained flight. Every satellite in low Earth orbit is perpetually losing altitude, slowly being pulled back toward the planet by the thin but ever-present atmospheric resistance. To counteract this, operators perform periodic propulsion burns, small engine firings that boost a satellite back up to its intended orbit. The amount of propellant available for these maneuvers is what ultimately determines a satellite's operational lifetime. When drag suddenly spikes during a storm, satellites are forced to burn more propellant just to stay in place. In more extreme cases, they can lose altitude faster than their propulsion systems can compensate, leading to a premature and uncontrolled re-entry into the atmosphere. This is not a theoretical danger. It is a risk that has already materialized at scale, affecting one of the most advanced space operations companies in the world. In February of 2022, a relatively modest geomagnetic storm resulted in the loss of approximately 40 Starlink satellites shortly after their launch by SpaceX. The event was classified as a G1 to G2 storm, precisely the kind of moderate disturbance that agencies like NOAA are currently forecasting. It was not an extreme or historic event, just a period of elevated activity during a solar cycle that, at the time, most people were not closely watching. This incident serves as a stark and recent reminder of our vulnerability. The satellites had been deployed into a low insertion orbit, which is a standard and responsible practice for SpaceX. The strategy is to place newly launched satellites at a lower initial altitude, which allows for the controlled deorbit of any units that fail their initial system checks. This prevents defective hardware from becoming long-term space debris. Under normal space weather conditions, this engineering choice works exceptionally well. But on that particular day, in February 2022, the storm-enhanced atmospheric drag was so significant that it prevented the majority of the newly deployed batch from reaching their operational altitude. They lost too much energy to recover and burned up in the atmosphere only days after their launch. That single event represented a loss of tens of millions of dollars in direct hardware costs, not to mention the associated launch expenses and the opportunity cost of replacing satellites that were meant to be expanding the constellation. SpaceX was able to absorb this loss without a major impact on its operations, thanks to its enormous manufacturing pipeline and its ability to replace inventory faster than any other space company in history. Nevertheless, the incident served as a powerful wake-up call for the entire industry. It demonstrated in clear financial terms that even modest space weather events can trigger catastrophic losses under the right set of circumstances. It compelled every constellation operator to fundamentally reconsider their models for space weather risk. The current geomagnetic storm, even at its baseline forecast levels, is not expected to cause losses on the scale of the February 2022 event. I want to state this clearly to avoid any unnecessary alarm. The conditions, while significant, are different. For the coming weekend, there are fortunately no new satellite deployments situated in the most exposed and vulnerable altitude ranges during the expected storm window. This means the unique combination of factors that led to such significant losses in February of 2022 is not currently in place. Today, operational satellites at their designated altitudes possess far greater margins to accommodate moderate increases in atmospheric drag. Furthermore, constellation operators have become more adept at scheduling their launches to avoid predicted periods of intense solar activity. But the fundamental principle has not changed, and it is this principle that is crucial for understanding the larger landscape of risk. Geomagnetic storms invariably generate drag, and this drag causes orbital decay. In turn, orbital decay reduces the operational lifespan of a satellite by forcing it to consume propellant that would otherwise be reserved for essential maneuvers, including the increasingly vital collision avoidance burns required as our orbits grow more crowded. Every storm that sweeps through the near-Earth environment exacts a price, a cost that accumulates over time. Even when these costs are not dramatic enough to make headlines, they are still felt. For the operators of today's vast satellite constellations, the impact of moderate storms appears in ways that are rarely reported. A Starlink satellite that was designed to function for 5 years might see its operational life cut to just 4 years and 8 months, simply because storm-induced drag forced it to use its propellant reserves more quickly than planned. When you multiply this small loss across thousands of satellites managed by numerous operators over decades of what may be unexpectedly active solar conditions, the result is a cumulative cost that is genuinely substantial. Yet, this cost is distributed so widely that it becomes difficult to attribute to any single space weather event. The financial implications are already visible, with insurance premiums for satellites in low Earth orbit rising as a direct consequence. Launch schedules, which 5 years ago paid little mind to such things, now incorporate space weather forecasts as a critical factor. The very economics of operating in low Earth orbit have been quietly rewritten by a sun that is proving more active than anyone had anticipated. There is also a secondary effect to consider, one that introduces a different kind of danger. The increased variability in atmospheric drag makes orbital position predictions significantly less accurate. This is a critical problem because every satellite's location is calculated using models that rely on certain assumptions about atmospheric conditions. When a storm unexpectedly alters those conditions, the predicted positions begin to diverge from the satellite's actual locations in space. Under calm solar conditions, these predictions can be accurate to within a few meters over several days. During a storm, however, the same prediction models can accumulate uncertainties measured in kilometers over the same period. Effective collision avoidance is entirely dependent on knowing precisely where every object is. When the position of every object becomes fuzzy and uncertain, the overall risk of a collision increases for everyone, even if no single satellite is in immediate, predictable danger. This brings us back to the central thread connecting all these phenomena. The Sun's dual X-class flare just this morning was a powerful demonstration of the raw energy this current solar environment can unleash. The presence of 3 loaded delta regions on the solar disk suggests that more events are likely in the coming weeks. The infrastructure that must endure these consequences has never been more exposed, for a simple reason. We have never had so many assets in low Earth orbit, and never before have those assets been so reliant on consistent atmospheric conditions for their survival and operation. The satellites themselves represent the most fragile link in our space-based infrastructure. This is not because they are poorly designed. On the contrary, they are, by and large, beautifully engineered systems. They are the weakest link because there are now so many of them, all operating so close to the very edge of what atmospheric conditions permit. As a result, Any significant disturbance to those conditions creates measurable operational stress across the entire constellation ecosystem. A single major storm from the current solar configuration, if its magnetic orientation, the BZ component, cooperates in just the wrong way, could cause drag to spike to extreme levels, producing satellite losses that would make the February 2022 incident seem modest in comparison. While the event this weekend is not expected to be that storm, the conditions that create such tempests are present on the Sun right now. The next few weeks will reveal whether one of them fully develops. Beyond the drag on individual satellites lies a broader concern, one that has been debated in space situational awareness circles for years and has now become genuinely urgent as orbital populations have exploded. This is the crash clock problem. The risk of collisions in low Earth orbit is known to increase during geomagnetic storms, and the cascading consequences of a major collision could generate effects that persist not for years or decades, but potentially for generations. It is the kind of risk that sounds abstract and distant until you take the time to sit with the mathematics, and when you do, it ceases to be abstract very quickly. Each satellite in low Earth orbit is meticulously tracked by space surveillance networks. This effort is primarily led by the United States Space Force's global network of radars and optical telescopes, which is supplemented by commercial tracking operations and data from allied nations. These networks constantly calculate close approaches, known as conjunctions in the technical literature, and predict potential collisions. The lead times for these warnings can range from days in advance for well-characterized objects down to mere minutes for fast-moving or recently launched hardware. This entire system is a vast, continuously running exercise in celestial choreography, a monumental effort to prevent tens of thousands of objects from colliding in a volume of space where even small differences in velocity translate to catastrophic releases of energy upon impact. Under normal, quiet conditions, this intricate system functions remarkably well. Satellite operators receive conjunction warnings whenever the predicted minimum distance between two objects falls below established safety thresholds. In response, they execute small, precise orbital adjustments, moving their satellites safely out of the potential collision window. These maneuvers have become a routine part of operations in space. Starlink alone conducts thousands of such collision avoidance maneuvers every year, quietly and without public notice, because the system is designed to handle this kind of operational overhead. The majority of these maneuvers are precautionary, based on statistical probabilities rather than a certainty of impact, but the cumulative effort involved is a testament to the constant vigilance required to manage our increasingly crowded skies. During a geomagnetic storm, a cascade of interconnected problems unfolds, severely compromising the entire system for avoiding orbital collisions. One of the first consequences is that many spacecraft enter a self-preservation state known as safe mode. This protocol is designed to shield sensitive electronics from the harmful effects of energetic electrons, which can cause surface arcing and charging events. However, in doing so, it deliberately shuts down non-essential systems, including attitude control. A satellite in safe mode is effectively adrift, prioritizing its own survival over its operational duties. This raises a critical dilemma. If a warning of an impending conjunction arrives while the spacecraft is in this protective state, its operators are powerless to command a maneuver. Compounding this challenge, the storm also disrupts the very communication links used to manage these assets. Ionospheric disturbances can degrade the uplink and downlink channels, creating interference similar to radio blackouts. For satellites that remain fully operational, the ability to receive commands or transmit status updates can be hindered just when it is most needed. A command that would normally take seconds to transmit might now take minutes, and vital telemetry could be lost or require retransmission, slowing the entire operational loop. Perhaps the most insidious effect, however, is how storms introduce uncertainty into the very fabric of orbital mechanics. The intense energy heats and expands the upper atmosphere, altering atmospheric drag in unpredictable ways. As a result, the models that predict a satellite's future location begin to diverge from reality. The uncertainty ellipsoids, the three-dimensional zones, where a satellite is predicted to expand dramatically. A potential collision that once appeared to be a comfortable miss can suddenly become a high-risk event, making the entire orbital picture dangerously unclear. When these three factors, unresponsive satellites, degraded communications, and unpredictable orbits converge, they create a situation of immense operational difficulty. The brief windows of opportunity for executing collision avoidance maneuvers, already short under normal circumstances, can shrink dramatically. Operators who typically have minutes or hours to respond to a conjunction alert may find their time severely curtailed. This can happen because the storm itself delayed the initial detection of the threat, or because the storm's effects have slowed their own ability to confirm the satellite's status and issue commands. It is in these moments of high pressure and incomplete information that critical decisions must be made, with the stakes significantly elevated. This is precisely the environment where miscalculations and errors are most likely to occur. And in the unforgiving realm of low Earth orbit, a mistake does not simply vanish. Its consequences are persistent and can reverberate for a very long time. The legacy of a single orbital collision is the creation of thousands of new hazards. Each piece of resulting debris becomes an independent projectile, posing a fresh collision risk to every other satellite sharing that orbital path. We have seen this play out with devastating clarity. The collision in February 2009 between a functioning Iridium communications satellite and a defunct Russian Cosmos satellite generated a cloud of over 2,000 fragments, large enough to be tracked from the ground. 16 years later, many of those pieces continue to circle the Earth. Similarly, a 2007 Chinese anti-satellite test, which intentionally destroyed a weather satellite, produced an even larger field of over 3,000 trackable fragments. Hundreds of these remnants are still in orbit today and are projected to remain there for decades. Each such event doesn't just add to the problem, it multiplies the danger, creating a more hazardous environment for all subsequent missions and future generations. This escalating threat leads to a nightmarish scenario that has been seriously considered in space policy circles for over 4 decades. It is known as the Kessler syndrome, named for NASA scientist Donald Kessler, who first formally outlined the concept in a 1978 paper. The theory describes a tipping point. It begins when the population of debris in a particular orbital altitude reaches a critical density. At this point, the likelihood of debris colliding with other debris, creating even more fragments, surpasses the rate at which objects naturally fall out of orbit due to atmospheric drag. This triggers a self-sustaining chain reaction. Each new collision generates more debris, which in turn increases the probability of further collisions, creating a cascade that could continue until the entire orbital band is saturated with a lethal swarm of fast-moving shrapnel. Such a state would render that region of space effectively unusable for functioning spacecraft. The Kessler syndrome is not an instantaneous event. It is a process that would unfold over years or even decades. Yet, once this cascade begins, it is extraordinarily difficult to halt. The technology for removing existing debris is immensely challenging and expensive, while preventing the creation of new debris requires a level of global cooperation that has proven elusive. A Kessler cascade in low Earth orbit could make entire altitudes unusable for generations, potentially setting back humanity's presence in space by half a century or more. It is important to place this in the proper context. The recent geomagnetic storm, a G1 or G2 event, is not going to be the direct trigger for a Kessler syndrome cascade. A single storm of this magnitude will not, by itself, cause the kind of widespread conjunction failures needed to initiate such a chain reaction. What we are describing is not the acute risk posed by this specific weekend's solar activity. Instead, the true concern lies with the chronic risk that builds over time. Driven by a period of unexpectedly elevated solar activity, this is where our attention should be focused. The danger is not a single, isolated event, but the cumulative stress these repeated storms place on our increasingly crowded orbital environment. The cumulative effect of repeated geomagnetic storms, originating from a sun that is more active than anticipated, contributes to a broader risk profile that compounds over time. Every storm that forces satellites into a state where they cannot be controlled is a period where our ability to avoid collisions is diminished. Every storm that injects more uncertainty into orbital predictions is a storm where our assessments of potential conjunctions become less reliable. While the probability of any single storm causing a catastrophic collision is genuinely low, that probability is not the whole story. The true nature of this threat is statistical. When you consider the sheer number of storms over several years of heightened solar activity across thousands of satellites, the probability of at least one such disastrous conjunction occurring becomes considerably more significant. This is the statistical trap that deeply concerns space situational awareness professionals. It is not the fear of one single, predictable catastrophe, but the quiet, creeping danger of compounded probability in an environment where there is very little room for error. The story of risk is often one of accumulation, where seemingly negligible chances compound over time. This is the subtle danger we face now. The cumulative buildup of small probability risks, each one minor on its own, can combine across thousands of opportunities to create an outcome that any rational assessment would deem unacceptable. A low probability, high consequence event becomes far more likely than our intuition suggests when the number of attempts grows large enough. This is the situation presented by the current solar activity. The trio of active regions on the solar disk is generating repeated storms, increasing the cumulative probability of severe consequences for our infrastructure. Even if no single event is catastrophic, every new storm is another roll of the dice. Each period of degraded collision avoidance for satellites opens another window for something to go wrong. Every spike of uncertainty in orbital predictions creates another chance for a missed conjunction warning. The crucial point is that this unstable solar configuration does not produce just one event. It produces them repeatedly over weeks and months. This repetition accumulates risk in ways that forecasters, operators, and policymakers are still learning how to properly model. The dual X-flare served as a powerful demonstration of this potential. The real question that remains is how many more such demonstrations we will witness before this active period finally subsides. This heightened solar activity also has profound implications for human spaceflight, a vulnerability that warrants special attention. The International Space Station, orbiting at an altitude of approximately 400 kilometers, remains well within the protective bubble of Earth's magnetosphere. This magnetic shield provides substantial protection from solar energetic particles. While the station's crew does experience increased radiation during geomagnetic storms, the levels generally stay within operational limits. For the most intense events, they can also retreat to more heavily shielded areas of the station. The situation, however, becomes far more serious for missions that venture beyond low Earth orbit, a category of exploration that is rapidly expanding. Missions under the Artemis program, which are designed for lunar operations, will spend significant time outside the protection of the magnetosphere. In this environment, solar energetic particle events can pose a genuine and severe radiation hazard. Future human missions to Mars would face similar exposure, but for a much longer duration, elevating solar activity prediction from a helpful operational detail to a mission-critical capability. The current solar instability with its rapid development of major flares from multiple regions, illustrates just how difficult it is to predict the space radiation environment for crewed missions. Had Artemis astronauts been on the lunar surface during an event like this morning's dual X flare, they would have needed to seek shelter immediately. The timing of that response would depend entirely on accurate early warnings. The same uncertainties that make ground-based space weather forecasting a challenge also complicate radiation planning for these pioneering missions. This continued solar instability therefore increases the long-term exposure risks for missions that are now being planned and executed, all in the shadow of a solar cycle that refuses to decline on schedule. The central thread is that every major event from this configuration adds evidence to the case that solar cycle 25 is not behaving as predicted, a contradiction with implications far beyond any single weekend's geomagnetic storm. Turning our attention back to Earth, modern power grids are generally robust against minor geomagnetic storms. Events classified as G1 typically produce effects that grid operators can manage through routine adjustments. Even G2 events, which introduce more significant voltage fluctuations and may require active mitigation, still fall well within the standard operational capacity of the system. This resilience is by design, as infrastructure is engineered with space weather in mind, especially for grids at high latitudes where geomagnetically induced currents are most likely to form. The true concern is not these individual events, but rather the cumulative stress that repeated storms place on aging infrastructure. Transformers subjected to these currents do not usually fail immediately. Instead, they accumulate damage over many storm events. Each exposure produces small amounts of thermal stress and insulation degradation, slowly weakening the unit over time. Eventually, a transformer that has absorbed decades of minor space weather stress can fail during an event that, on its own, would not have damaged a new piece of equipment. Furthermore, the assumptions built into grid resilience models often date from earlier periods of solar behavior. If the current cycle is producing more frequent moderate events than historical baselines would suggest, then this cumulative stress is accumulating faster than infrastructure life cycle models anticipated. This is not an immediate crisis, but rather a slowly evolving vulnerability that becomes more apparent with each unexpected active period. The dual X flare was not just a one-off spectacle. It is part of a pattern of elevated activity that adds to the cumulative exposure across infrastructure systems, each with its own aging timeline and its own operational limits. This brings us to the part of the story where the sun truly breaks from the script we wrote for it. To understand this, we must step back from the immediate events and look at a pattern nobody expected to see right now. Solar cycle 25 officially began in December of 2019. At that time, NOAA's Solar Cycle Prediction Panel, drawing upon the best available solar dynamo models and the collective expertise of the solar physics community, issued its formal forecast. That forecast predicted a weak cycle, similar in amplitude to Solar Cycle 24, which had been one of the weakest in over a century. The prediction anticipated a maximum monthly smoothed sunspot number of approximately 115, expected to occur around July of 2025. Following this peak, the cycle was expected to decline gradually through 2026 and 2027, approaching its minimum sometime in 2030. That forecast, however, did not survive contact with reality. By 2023, solar activity had already soared past the predicted levels. Sunspot numbers were running substantially higher than the forecast, and major flare productivity was far exceeding expectations. It became clear the cycle was going to be significantly stronger than NOAA had projected. Consequently, in late 2023, NOAA revised its forecast upward. The new prediction called for peak activity to occur much earlier, between January and October of 2024, with a higher sunspot number than originally expected. The sun, it seems, had its own story to tell. Even this updated projection turned out to be an understatement. The sunspot maximum that was observed in late 2024 actually surpassed the revised forecast in intensity, and the output of major flares continued at an elevated level all through 2025. Now, as we find ourselves in late April of 2026, a time when the cycle should be in its declining phase, we are witnessing something remarkable. Instead of a gradual tapering of activity, there appears to be an intensification. With the most volatile magnetic structure of the entire cycle emerging this late, this development presents a puzzle that directly contradicts our standard understanding. Solar cycles are expected to follow a predictable arc, building toward a maximum over 4 to 5 years before fading toward a minimum over the next 6 to 7. The decline is supposed to be characterized by diminishing activity, with the most powerful events typically clustered around the cycle's rise and peak. A cycle that saves its most dangerous magnetic configurations for its supposed descent is not adhering to the established model. One possible explanation is that the cycle has not yet truly reached its zenith, and what we identified as the peak in late 2024 was merely the first of several. This phenomenon, known as a double-peaked or multi-peaked maximum, has been documented in the history of solar observation. If solar cycle 25 has a second peak yet to come, the heightened activity we see now might be the start of that next surge, rather than a strange anomaly during the decline. An alternative interpretation is far more humbling. Our models for predicting solar cycles are simply not as precise as we believed. This apparent failure in forecasting could reflect fundamental constraints on our ability to predict the sun's behavior more than one cycle into the future, a possibility that some solar physicists have been advancing for years. In either case, the observed solar activity in 2026 is at odds with the narrative of decline that shaped forecasts for much of 2025. Something is taking place on the sun that our models did not account for, and the current complex arrangement of 3 simultaneously active delta regions serves as powerful evidence of this unexpected turn. Whatever the underlying cause, the chance that the cycle has not yet peaked fundamentally alters how we should approach the current window of risk. This leads us to a fascinating idea, the false decline hypothesis. In the language of solar science, a secondary peak describes a second wave of maximum activity that appears after an initial peak has passed, usually separated by a temporary lull. While not every cycle exhibits this behavior, it has occurred often enough in the observational record to be recognized as a known pattern, not a singular fluke. The hypothesis for solar cycle 25 is that the peak we witnessed in late 2024 might have been only the first act. If this is correct, the current levels of activity could represent either a sustained period of high energy or the beginning of a secondary peak that will grow more defined in the months ahead. Under this hypothesis, we are not in the declining phase at all. Instead, we are in an extended phase of heightened activity. And the events unfolding now are not anomalies, but are entirely consistent with such a period. History provides a stark and compelling precedent for this kind of late-cycle drama. The Halloween solar storms, which occurred in late October and early November of 2003, took place during the declining phase of solar cycle 23. That cycle had reached its maximum in early 2001 and was well on its way down by late 2003. Despite this, that period produced some of the most powerful solar events of the entire cycle, including an X-28 flare, one of the largest ever recorded. These and other X-class events triggered extreme geomagnetic storms and caused tangible impacts on Earth's infrastructure, including power outages across parts of northern Europe. The lesson from the Halloween storms is profound. The largest and most hazardous events of a solar cycle do not always coincide with its designated peak. they can erupt during the declining phase. The physics that drives these major events, the slow buildup of complex magnetic structures in active regions, operates on its own schedule, unconcerned with our neat classifications of cycle phases. These timescales can produce outliers far from where we expect them. If solar cycle 25 is following a pattern similar to that of cycle 23, then the current phase may be far more active than the standard decline narrative would suggest. This raises a critical question. Could the cycle's most dangerous events still be ahead of us? The recent dual X-flare from region 419 and the concurrent appearance of 3 delta regions are consistent with this very interpretation, as this is precisely the kind of activity that characterizes late-cycle extreme events. But why would this happen? What physical mechanism could allow a solar cycle to unleash its most powerful moments during a phase when its overall activity is supposed to be fading? While this question lacks a definitive answer, there are several hypotheses worth exploring. To understand them, we must look deeper into the Sun's magnetic heart. The Sun's magnetic field is generated by a process known as the solar dynamo. This is a complex fluid dynamical engine operating deep within the convection zone, where hot, ionized gas undergoes differential rotation and turbulent motion. Over the course of an 1-year cycle, the dynamo transforms the kinetic energy of solar rotation and convection into magnetic energy, which then rises to the surface to form active regions and sunspots. One of the most intriguing, yet incompletely understood, aspects of this process is the concept of magnetic memory. The magnetic field at any point in the cycle is not just a product of the dynamo's current state. It also depends on the history of what the dynamo has produced in previous cycles. Residual magnetic flux from prior cycles can persist in the deeper layers of the convection zone, emerging much later in surprising ways. In a sense, the dynamo has a memory of its past actions, and this memory can influence its present behavior in ways that simple, single-cycle models fail to capture. This concept offers a compelling physical explanation for the anomalies we are currently witnessing. If solar cycle 25 is being influenced by residual flux from cycle 24, or even from cycles before it, then the current elevated activity might reflect a delayed release of energy from storage structures not visible in standard observations. The present multi-region instability, with its 3 simultaneous delta regions, could be partially fueled by this stored energy. This would create a magnetic configuration on the solar surface, far more complex than what the primary dynamo cycle would generate on its own. While our understanding of the Sun's inner workings is constantly evolving, some models remain speculative. Dynamo modeling, for instance, is a field of active research where different approaches yield varied predictions. One compelling concept is that of magnetic memory, which suggests the Sun's current state cannot be fully understood by observing this cycle alone. This framework offers a possible explanation for the unexpected configurations we are now witnessing. It posits that stored magnetic energy from previous cycles could be released late, potentially causing the multi-region instability currently observed. This raises a profound question. If the Sun has a memory, are we seeing the culmination of processes that have been building for much longer than a single 1-year cycle? Another idea gaining traction in solar physics proposes that active regions on the Sun are not as isolated as traditional models have assumed. This is known as the multi-region coupling hypothesis. It suggests that large-scale magnetic connections can span the solar surface, linking regions that appear to be separated by vast distances. These invisible tethers could allow an event in one area to ripple outwards, influencing conditions in another. Observational evidence for this includes the phenomenon of sympathetic flaring, where multiple active regions erupt in quick succession, despite being too far apart for a simple, direct cause. In some cases, these events have been traced to immense magnetic loops that connect the regions, allowing disturbances to propagate at incredible alphenic speeds fast enough to destabilize a connected region within minutes of an initial event. If the three delta regions currently on the Sun are intertwined in such a magnetic web, the implications are deeply concerning. A major flare erupting from one region could potentially trigger or contribute to instability in the others, creating a cascade of events. While the precise timing of such a coupled event would be impossible to predict, the overall probability of a rapid series of major flares from multiple regions would be significantly higher than if each region were evolving independently. Research into multi-region coupling is still in its early stages, with no consensus on how common or significant these interactions are. However, the current solar configuration presents a unique, real-time test case. Should we observe major events from several regions in close succession over the coming weeks, it would lend strong support to the coupling hypothesis. Conversely, if the events remain isolated, the theory would be less substantiated. The Sun may behave less like a collection of independent spots and more like a single connected system. To grasp the full weight of the current situation, we must look beyond the immediate events and see them for what they may represent. The dual X-class flares from region 4419, the resulting Earth-directed coronal mass ejection, and the approaching geomagnetic storm are all significant in their own right. They are real phenomena with consequences that will unfold over the coming days. Yet, as impactful as they are, they may not be the most important part of the story. Instead, they can be seen as a warning signal, a demonstration of the Sun's current potential. This forces us to shift our focus from what has already occurred to what might yet unfold. The truly critical question is what happens when one of the other delta regions, particularly the formidable region 4420, reaches the same threshold of instability that 4419 just crossed. The danger is magnified if this occurs while the region is positioned near the solar central meridian, a geometry that provides a direct line of sight to our planet. A major X-class flare from region 4420 during its transit through this geo-effective zone would launch a coronal mass ejection aimed almost squarely at Earth. If that CME is driven by a powerful shock front, as the recent event was, it could traverse the distance to Earth in a mere 24 to 36 hours. The potential for escalation is significant. Should such a CME arrive while Earth's magnetic field is already disturbed by ongoing solar activity, the interaction effects could be compounded. This could produce a geomagnetic response far exceeding baseline expectations for a single event. It is important to state that this is not a prediction that a catastrophic event is imminent. Rather, it is an assessment that the underlying conditions for such an event are currently in place. The solar configuration, with its multiple delta regions, has already demonstrated its capacity for rapid, high-energy events. This analysis is based on pattern recognition applied to the available observational evidence. The Sun is exhibiting behavior that was not anticipated for this point in the solar cycle. It has multiple active regions capable of repeating the powerful display we have just witnessed. At least one of these regions is now rotating into a position where any repeat performance would have direct consequences for Earth. This is not alarmism. It is a sober acknowledgement that the risk window is elevated. We are not in a period of solar quiet. We are in a phase of continued, heightened activity that official forecasts did not predict and that the scientific community is still working to understand. During such a time, the solar disk warrants more careful observation than it might have 6 months ago, simply because the conditions for escalation are present in a way they rarely are. To separate established fact from informed speculation, it is helpful to summarize what we know for certain at this moment. We know that on April 24th, 2026, active region 4419 produced 2 X-class flares within just 7 hours. an unusual clustering of high-energy events from a single source. We also know that the second of these flares launched a coronal mass ejection with a shock front measured to be moving at approximately 1,293 kilometers per second. Furthermore, modeling from NOAA has confirmed that this CME has a component directed toward Earth. Based on this data, the CME is expected to arrive sometime during the late hours of April 25th through April 26th. The baseline forecast is for G1 minor storm conditions, with the possibility of escalation to G2 moderate storm levels if interaction effects amplify the geomagnetic response. These are the facts upon which our current watchfulness is founded. At this moment, our view of the Sun reveals a complex and unsettled state. 3 distinct Delta-class magnetic regions are currently visible on the Earth-facing solar disk. Among them, active region 4420 stands out. It is the largest of the trio and has been steadily growing in magnetic complexity over the last few days as it rotates toward the central meridian. Alongside it, region 4423 is a new arrival, characterized by its rapid development and an already present delta structure. This configuration of multiple, highly active regions is noteworthy, as it is generating coordinated activity across separate areas of the Sun, a stark contrast to the isolated events typical of a quieter solar phase. This heightened activity fits a broader pattern. Since 2023, solar cycle 25 has consistently surpassed original predictions. The current surge in late April of 2026 directly challenges the narrative of a declining solar cycle that had shaped forecasts throughout 2025. Such late-cycle bursts are not without precedent. Secondary peaks have been recorded in past cycles, and the infamous Halloween solar storms of 2003 serve as a powerful reminder that extreme events can indeed occur late in a cycle. This solar reality is mirrored by an unprecedented terrestrial vulnerability. Our global infrastructure has never been more exposed to the effects of space weather. Low Earth orbit is more crowded with satellites than ever before. Our power grids rely on long-distance transmission lines susceptible to geomagnetically induced currents, and the communication and navigation systems that underpin modern life, from global positioning to financial transactions, depend on a stable ionosphere, the very layer of our atmosphere that geomagnetic storms can severely disrupt. This is the factual landscape we are navigating: a Sun that has already acted, a coronal mass ejection that is already on its way, and the clear potential for more activity to come. Against this backdrop of established facts, we must also confront the significant scale of what remains unknown. These uncertainties are not trivial. They profoundly shape how we must approach the current risk. For instance, it is unclear if the coronal mass ejection from the X2-5 flare will merge with the earlier CME from an M-class event already in transit. We cannot know the crucial BZ orientation of either CME individually or combined when they reach our planet. Another variable is a high-speed stream from a coronal hole. Will it arrive in time to amplify the geomagnetic disturbance, or will it pass by without any meaningful interaction? Looking back at the Sun, we question whether active region 4420 will unleash another X-class flare as it crosses the geo-effective zone, or if it will traverse this critical area with only minor activity. The future of the new region 4423 is equally uncertain. How long will its rapid development continue? What level of magnetic complexity will it achieve? And will it evolve into a major source of flares or quiet down? On a larger scale, we are unsure if this period of heightened solar output marks a genuine secondary peak for cycle 25, or if it is merely a temporary surge within an overall decline. The very nature of the multi-region configuration is a puzzle. Does it hint at deeper dynamo processes within the Sun, or is it simply a coincidence of several regions emerging at once? The duration of this active period is another open question, as is the behavior of any future event until it actually happens. While space weather forecasting has made immense strides, it is still constrained by the fundamental physics of the Sun and the limits of our observations. These unknowns are not simply gaps that new instruments will quickly fill. They represent deep, inherent uncertainties in solar and solar wind behavior. Ultimately, what we do not know defines the risk profile as much as what we do. The range of potential outcomes in the coming weeks is vast, and our models cannot yet tell us which future we are heading, into one where region 4420 remains stable, or one where it produces a major, Earth-directed event. It is important to frame this situation correctly. The initial event, the dual X-class flare from region 4419, is now in the past. Its consequences have been set in motion. A coronal mass ejection is traveling toward Earth, and a geomagnetic response is expected this weekend. Nothing can alter this course of events. In isolation, this incident is not expected to cause a major crisis. The baseline forecast points to G1 to G2 storm conditions, which our infrastructure is generally designed to withstand, even if interaction effects push the disturbance higher. However, the true story is not the event that has already occurred. The real significance lies in the risk window we have now entered. The Sun's current state, with 3 active delta regions and a proven ability for rapid, major flare production, creates an environment where more significant events are plausible in the coming days and weeks. Should one of these events originate from a region directly facing Earth, the resulting impacts could be far more severe than what is anticipated for this weekend. This is not a forecast of what will happen, but rather a characterization of the current risk environment. The Sun has provided a clear demonstration of its capabilities. How we respond to this demonstration, how diligently we monitor for further instability, and how seriously we consider that solar cycle 25 may not have peaked, will determine its legacy. Will it be a valuable warning, or will it be dismissed as an anomaly, leaving us unprepared for the next, more significant event? This story, therefore, does not conclude with the coming weekend's storm. The very solar configuration that produced the recent flare remains in place. Solar rotation is steadily carrying the most hazardous active region into the most geo-effective alignment over the coming weeks. The potential for interactions between multiple CMEs, which could amplify their impact, is a tangible possibility. Furthermore, the established history of solar cycle 25 surpassing predictions, combined with the fact that our technological infrastructure is more exposed than at any point in history, creates a complex risk landscape. This narrative is still unfolding. The next several weeks will be a critical period of observation, where we will either witness additional events from this dynamic setup, or watch as the active regions gradually stabilize and rotate out of view. The outcome remains genuinely unwritten, a story that will be told day by day under our watchful gaze. The evidence provided by the Sun this morning is compelling, suggesting the conditions for a much larger event are now in place. What we witnessed could be seen as a preliminary sign, a demonstration of the immense power our star currently holds in reserve. The Sun's magnetic fields remain highly energized, and its constant rotation is steadily bringing more of these volatile active regions across the central meridian. This movement raises an important possibility. Any subsequent events could be far more directly aligned with our planet than today's was. The critical question, therefore, is whether the next powerful release of energy will occur when its source is pointed directly at Earth. We continue to watch, reminded that our world is always within the Sun's powerful sphere of influence.